Today we are going to look at a paired t-test. Today we start another two-sample t-test called a paired t-test, sometimes called a matched pairs t-test. Here the samples are paired for some reason. Either it's the same person with before and after, left, right hand, pre-test, post-test, books or notebooks. Or linked people, for example, husbands and wives or twins. You have two different measurements for the same person, or the measurements will be linked in some way. The two samples are paired in the same way and cannot be independent. The basic idea of a t-test is you take the differences in the measurements. The differences are your data, so you put those in list 1. And you treat the differences as a one-sample t-test of means, a t-test on the differences. It's number 2 in your calculator under tests. The name of the test is a paired t-test. Our hypotheses are the mu differences, for the null hypothesis, the mu differences equals 0, versus the mu differences greater than 0, less than 0, or not equal to 0 for the alternative hypothesis. Our conditions should be checked for hypothesis test and confidence intervals. The samples must be paired or matched, and you must address this. The n sample differences can be viewed as a random sample from the population of differences, and the population of differences distribution is normal or approximately normal, or large enough, meaning greater than or equal to 30, or you have an NPP of differences that is fairly straight. So it's plausible that the data come from a normal distribution. This test statistic is T equals the mean, the differences minus the population mean, all over the standard deviation of the differences divided by the number of differences we have. The degrees of freedom is n minus 1. The name of the confidence interval is a paired t-interval. The formula is the mean of the differences plus or minus t star divided by the times the standard deviation of the differences divided by the square root of the number of differences, where t star is your t critical value. For our confidence interval, we are estimating the mean of the differences. Let's look at this example, marriage ages. Below is a table concerning the ages at marriage for a sample of 24 couples that obtained their marriage licenses in Cumberland County, Pennsylvania. So we have the 24 couples, the husband's age and the wife's age in years. You need to calculate the differences. Husband minus wife. For each couple in the sample, subtract the wife's age from the husband's age. Record the results in the table. Enter the set of differences in your calculator. Use your calculator to compute the relevant summary statistics regarding the sample of age differences. Record the summary statistics along with the symbols used to represent them. Create an NPP, normal probability plot, of the differences in ages for the 24 couples. So I want you to pause the video now and do that. Then I want you to do a complete significant test of whether the mean of the population of age differences exceeds 0, suggesting that the husband tends to be older than the wife. Are your results statistically significant at the 0.05 level? Then find a 90% confidence interval for the mean of the population of age differences. Comment on whether the interval contains 0, and then write a short conclusion about the difference in ages between husbands and wives based on your analysis of the data. This example will illustrate a paired comparisons experimental design. One can control some variation in marriage age is by considering couples rather than individuals. A less sensible design for this study would have been to obtain the ages of one sample of 24 wives and of a separate sample of 24 husbands. One analyzes paired comparisons data by analyzing differences using the inference procedures you've studied concerning a population mean. In this case, the mean of the population of age differences is what one makes inferences about. So for your data, you should have found the differences in our ages. This is an example of the normal probability plot you should have done. We have a mean of 1.875 and a standard deviation of 4.812. And then you could go through and run your t-test and your confidence interval so that you have everything for your complete work of the hypothesis test and confidence interval. So you do still need to go through the process of this, not just finding the information, but actually writing it out. So the name of this is a paired t-test. My mean of differences is the mean difference in age, husband minus wife. My null hypothesis is my mean difference equals 0. My alternative hypothesis is my mean difference is greater than 0. Evidence for my alternative hypothesis is the mean difference of my sample is 1.875, which is greater than 0. The data is paired, husbands with wives. This must be addressed. We assume the data was collected randomly. And represent the population of Cumberland County, Pennsylvania. The NPP is reasonably straight. So we can assume the population of differences distribution is approximately normal. So now we're going to find T. Our formula is the mean of the differences minus the population mean of the differences all over the standard deviation of the differences divided by the number of differences we have. So we'd have 1.875 minus 0 all over 4.812 divided by the square root of 24. We get about 1.909. Our alpha level is 0.05. Our degrees of freedom is 24 minus 1, which equals 23. We get a p-value of 0.0344. Our p-value is less than our significance level, because 0.0344 is less than 0.05. So we reject our null hypothesis. There is evidence to suggest husbands tend to be older than wives in Cumberland County, Pennsylvania. Now we can go ahead and find our 90% confidence interval to estimate the mean differences. Our conditions have already been checked. In our hypothesis test. So our formula for our confidence interval is the mean of the differences plus or minus t star times our standard deviation of the differences over the square root of the number of our differences. So this would be 1.875 plus or minus 1.714 from our table times 4.812 divided by the square root of 24. Again, remember our degrees of freedom is 24 minus 1, which equals 23. Our confidence interval ended up being 0.191 to 3.559. So we are 90% confident. The mean age difference is between 0.191 and 3.559 years. The interval does not contain 0. So 0 is not a plausible difference. And this is consistent with our hypothesis test results.